Hello everyone and welcome to the Section 4 bonus examples of abstract modern algebra. So we have two problems that we're going to look at that have some real life applications to what we've been looking at in permutations and cycles. So I was hoping that both of these problems might could give you a little more visual of how these could be applied in real life. So let's take a look at our first bonus problem. We have a plant with a water delivery system set up for different locations in the plant. One system has a valve control that sends the fluid in two directions, so let's call it 1 and 2, and there are different pumps used for each process and valves are used to separate the fluid going into these processes. So all processes will let the water go into a water treatment system before being delivered back to the county. So say you were asked to design a system that could open and close the valves for what processes are required to be run. And you can let the system automatically know by describing each process as permutation cycles. So figure out the cycles you could use. And we can see the figure below for the plant setup and processes. So let's look at the figure here. So we have our two flow directions at the beginning, 1 and 2. Looks like when flow direction 1, we have 3 different pumps and processes and valves that separate whether the fluid goes into them or not. And in the second direction, we have 2 processes with valves to separate them. And of course, all the processes go to a water treatment, which will take the water back to the county. Of course, in terms of permutations, we can consider this as cycling back to 1 or 2, because technically the county will bring the water back to the plant in the end. So let's take a look at the process here and describe it using cycles. So 1 and 2 is describing our flow direction already. So let's look at our diagram here. Let's label this process as 3, this one is 4, and this one is 5. And let's label our water treatment as 6. And then let's label this as 7 and this one as 8. Okay, so these cycles we will use we have 1, 3, 6, and this is only process 1. Because if you look at this cycle, if we were to describe if we were to let our system know that we need the valve open in direction 1 and only process 3 open, we could describe it as 1, 3, 6, because we have the flow going to 1, or going from 1 to 3, and then it goes from 3 to 6 to the water treatment. And then, of course, it's understood that 6 would go back to 1, just like what we were saying, the water will go back to the county and it'll cycle back to 1. And we'll do the same thing for process 2. We have 1, 4, 6 for only process 2. And then we can do 1, 5, 6 for only process 3. And we can do 1, 3, 6, 1, 4, 6 for processes 1 and 2. And then we can do 1, 3, 6, 1, 5, 6 for processes 1 and 3. And then we can do 1, 4, 6, 1, 5, 6 for processes 2 and 3. And then if we were to want all 3 to be open, we can do 1, 3, 6, 1, 4, 6, and 1, 5, 6 for all 3 processes. And this is all for flow direction 1. Okay, now let's look at flow direction 2. So for flow direction 2, we can do 276, and this is only process 5. I'll make sure I'm keeping my labels consistent. Yep, process 5. And then we can do 286 for only process 6, and then we can do 276, 286 if we are going to do both processes. And this is for direction 2. And yeah, that's pretty much all there is for this problem. These are the cycles that we would use if we were to want the system to know which valves should be open and which ones should be closed. So, all right, let's take a look at the second problem. So suppose we have a 24 blade ceiling fan and it's being designed for air circulation. So the blades have 6 different pitch angles that need to be distributed evenly across the fan to keep the system balanced and to help reduce resonance and noise. So we need to come up with a design using disjoint cycles that satisfy these design parameters or these design requirements. So let's take a look at what we got here. This is just a little diagram of a fan. Of course, it's not a 24 blade fan. Those fans do exist, but very likely, probably very likely see one smaller. This is just a 6 blade fan, but I thought it would be a neat little diagram to give this problem a little more character. So let's take a look at what we got here. We have 6 different blade angles. So we will have 24 divided by 6 equals 4. So we will have 4 cycles to describe the distribution of these different blades. So we can use spacing of 6 for each cycle to evenly distribute the blades. So what that means is we can do a cycle like 1, 7, 13, 19. So basically we have 1, add 6, we got 7, and then add that 6 of that, we got 13, add it again, we got 19. So that's 1 4 cycle. And then we can do 2, 8, 14, 20. And the reason I'm using the commas is because we're using double-digit numbers, because if we don't use the commas, it can get kind of confusing seeing the numbers jumbled together to know which one is a single-digit number and which one's a double-digit. And then we have 3, 9, 15, 21. And then we have 4, 10, 16, 22. And we can have 5, 11, 17, 23. And then for our last one, we can have 6, 12, 18, 24. And these are our disjoint cycles that we can use that. And as you can see, it evenly distributes the 6 blades along the, or 6 different blade designs across the 24 positions that we have on the fan. And we can write these using disjoint cycles because the way a fan rotates, see, like if we were looking at the 6 blade diagram up here, if the fan was to cycle around, spin around, the first blade would eventually cycle back to its position. But when it rotates n number of degrees, it'll probably get to the second position or so on and so forth. But that's the reason why when designing a fan, designing blades, we can use permutation cycles to describe it. All right, that is it for the bonus problems for, or at least for these first bonus problems for section 4 of abstract algebra. Thank you so much for watching and hope you guys enjoyed. Please leave a like and comment if you have any thoughts. Thank you.